So hello, everyone. I'm Matthias. Thank you for coming to this talk about defense against adversarial example with some provable guarantees. So you probably all know that already, but recent progress in machine learning, and in particular deep neural networks, have led to them having really good performance at many tasks. And because of that, they're increasingly deployed, including in attack-prone contexts. And a recent example of that is when Taylor Swift was using facial recognition at her context to identify stalkers, for instance. And in the same article that I showed here, they say that big companies like Ticketmaster are investigating actually replacing tickets with face recognition. So let's use that last one as a running example and see how it could work. So let's say I arrive at a concert and I face a camera. The camera is ingested in a deep neural net, and it scores my face for each ticket. And you know, to start with, the network works pretty well. So if I show up without a ticket, the top score given by the neural net will be no ticket, and I won't be granted access. However, it's been shown times and times again that these deep neural networks are very vulnerable to a type of attack called adversarial examples, in which the attacker does a small change to the input. So in that case, maybe it's like some very light makeup that I designed, or a hat that casts some special shadow on my face. And this very small change triggers a drastic change in the scores given by the neural net, so that I'm now recognized as the proud owner of ticket 2, and I'm granted access. And you know, this type of attacks works really well basically against any input in many contexts. So here is an example of the ImageNet network released by Google for the ImageNet dataset. And what I'm showing is the accuracy under an increasing size of adversarial example attack. And what we can see is that under no attack, the network has roughly 78% of accuracy, which is pretty good for that data set. But as soon as the attack starts, the accuracy completely collapses to 7% for attacks up to size 0.5 and 1% of size 1. And to give you an example of what it means, this is how with an attack of size 0.5, you can turn this giant panda into a teddy bear, and with an attack of size 1, you can turn it into a teapot. And basically, the changes are invisible to the naked eye. So I think given those results, if we're deploying such a model in an attack-prone context, we shouldn't really treat it as if it had 78% of accuracy, but more like 7% or even 1%. And so in that case, I think a key question is there any accuracy we can rely on under attack? And there's been quite a lot of work recently into trying to answer that question. And most of it has been with best effort approaches, where, as we've just seen, we can actually run an attack to try to evaluate how robust a model is under such attacks. And if we want to improve this robustness, well, we can try many approaches. One of the popular ones is to keep training the model on attacked images to try to make it better at classifying them. But the big problem is that both those steps are attack-specific, which led to an arms race between attacker and defender, which basically attackers have been winning. So I think the key questions we want to answer is, first, can we guarantee any accuracy? Like, can we say for any attack below that size, this is the accuracy you can rely on? And second, maybe even more important, can we, for a given prediction, say how hard it is to attack? Why is that second one important? Because in this access control example, maybe when the prediction is robust, it's hard to attack. You can let the person in automatically, but if the prediction is not robust, a guard can come and check the actual concert ticket. Now, you may have heard about a few recent work to answer those questions with provable guarantees, but the key challenge is that they don't scale well in terms of 3 dimensions: the input size, the size of the neural network, and the size of the training data. And given the recent trend of training larger and larger models on bigger and bigger data sets, it means that we can't use them on the models we actually want to use for the tasks at hand. So my defense that I call PixelDP gives provable guarantees of robustness for norm-bounded attack using a different approach based on a privacy mechanism called differential privacy. And it turns out that this approach is by far the most scalable, and for the first time we were able to give guarantees of robustness for large models on ImageNet. So let's see a bit how we can design a deep neural net for which we can prove some robustness guarantees. So as we saw in the example, the key, the core of the problem is that a small change to the input of the neural net can trigger a drastic change in the scores. And here we'll define a small change as the size of the change made by the attacker is below size we can parameterize in 2 norms, so the regular Euclidean distance in pixel space. And the key idea is to design a deep neural net where we can bound how much the scores can change under arbitrary small changes to the input. And this is where we leverage differential privacy. So differential privacy is a technique to randomize a computation, typically made on a database, such that changing one row of that database leads to bounded changes in the distribution over possible outputs. So intuitively, if you're trying to count the number of people in a database with a given attribute, adding or removing one row can only change that count by at most 1. So if you add a bit of noise and observe the result of that algorithm, it's hard to say if it was computing on the database with or without the extra person. And this is this bound on what you can learn is what's expressed in this differential privacy formula. Now, is that enough to prove some robustness for deep neural net predictions? Well, not quite, because we have a randomized mechanism, so it would be like randomized prediction, and then we have a guarantee on the probability, but that's not quite what we want. However, for a differentially private mechanism with bounded outputs between 0 and 1, like the scores given by those neural nets, what we can prove is that the expected score also follow the same bounds, and this is what we can use to bound how much scores can change under arbitrary change to the inputs. So just to summarize a bit what I've just said, we can make this prediction function, the deep neural net, differentially private, and then we need to predict the expected scores of that function. And with the result I just showed, we can bound for arbitrary changes to the input how much the scores can change. Why is it interesting? Because if those bounds don't overlap, we basically prove the prediction is robust to arbitrary attacks below a given size, because the best the attacker can do is lower the top score to this lower bound and increase the other scores to their upper bound. And because they don't overlap, it's not enough to change the top score or the prediction. Now, I kind of said, oh, make this prediction function differentially private, then predict the expected score. How can we do that in practice? Well, the first thing is to make it differentially private. So we have to add some noise in the computation that we do with a noise layer that ensures that this first part of the computation up to the noise is differentially private. Now, this second part is actually only a post-processing of a differentially private output. And there's a well-known result in differential privacy that it's resilient to post-processing. So now the scores, the final scores given by the neural net are also differentially private. And the other thing that we need is compute the expected output of this neural net. Unfortunately, we have this very complex post-processing, so we can't do that analytically. So we'll just use a standard Monte Carlo estimate where we run the model many times, compute the average, except now it's not the true expectation, so we need to add some confidence intervals where we know the true expectation is with high probability. We include that in our bounds, and if they still don't overlap, we prove that the prediction is robust. Now, there's still many challenges to get actually good predictions out of this model. I won't have time to describe them today, but there's one I want to focus on a bit, which is scale. So I told you we could scale to ImageNet, which is a fairly high resolution classification data set for large models like this Inception model released pre-trained by Google. So how can we do that? Well, it was released pre-trained by Google, so it would be nice to be able to leverage that work already done and use it as is, right? Well, it turns out that what we can do is train what we call an autoencoder. So it's a model that just tries to recreate its own input, so try to learn the identity function, except now with our noise layer. We train a very small one on ImageNet, so it's very fast, like much faster than training Inception from scratch. And then we can just stack it in front of that pre-trained model. We need to do a few steps of training again, like a fine-tuning steps, but much less than to retrain from scratch. And this is where like the magics of differential privacy happens, where now all this giant computation that goes through an entire model is only post-processing. So the guarantees we added carry up to the end of the model, and we have the same guarantees as before. And that's actually how we could support ImageNet. Cool, so now let's see a bit how it works. So we evaluated pixel DP, like trying to answer many questions. Today, I'll touch on 3 of them, which is like, well, can we guarantee any accuracy under attack for ImageNet? Are those robust predictions harder to attack in practice, and how does it compare with existing methods? And we run that evaluation on 5 data sets, 3 models, looking mostly at the accuracy we can guarantee, and then the accuracy under attack. And for that last one, we used the state-of-the-art attack and strengthen it for our method because to take into account the fact that we had noise in the computation. So first, this is the results we get on ImageNet. The baseline is the pre-trained version that we released, and this shows 2 pixel DP models with increasing noise. And the main takeaway is that we can guarantee an accuracy of 40% for arbitrary attacks below size 0.2. So, and just to be clear, that's the models and data sets orders of magnitudes larger than what we could do before. So that's pretty great. Now, would I deploy that in my access control example? Well, like 40% is still pretty low, so maybe not yet. There's still work to be done, maybe. But what I also said is that if we could guarantee or if we could measure the robustness of any single prediction, what we could do in that context is just say, well, if the prediction is robust, I can let the person in, and if it's not robust, maybe a human can come in the loop. And in that case, what we care about is the robust accuracy only on those, is the accuracy under attack only on those robust predictions. So this is what I show on this graph for a robustness threshold of size 0.05. And what we can see is that compared to the baseline, the undefended model, those robust predictions are much harder to attack. So we still get a pretty good accuracy of 80% for attacks of size up to 0.4. Now, there's some predictions that are not robust, so we are not going to be able to let the person in automatically in the concert. How many is that? Well, we can still make robust predictions for about 70% of all the images. So that's pretty good. And of course, what we can do is increase that robustness threshold, in which case we'll make less predictions, like around 40% here, but they'll be even harder to attack. And what we see is that the accuracy under attack is even higher than before. And just to do a quick comparison, some best effort attacks that work well in practice but don't have this property of being able to say for a given prediction how hard it is to attack. mean that they cannot distinguish between more robust and less robust prediction, and so get less accuracy under attack. And finally, just to quickly talk about scale, this is a comparison with the state-of-the-art robust defenses at the time. And what we can see is because with PixelDP, we are able to train much larger models, we can get both like better accuracy and more robust accuracy under attack. So to summarize, PixelDP is the first defense that both gives attack-independent guarantees for arbitrary attacks under a given size and scales to the largest models and data sets. And what I'm pretty excited about is that there's already quite a bit of follow-up work where people either increased the bounds at a given noise level or looked at other noise distribution, how to adapt optimization. So I'm hoping that this is a new direction for defenses against adversarial examples. So on that note, thank you for coming, and I'm happy to answer questions.
So thanks. So other questions in the room? Please come to the microphone and ask. Could you move a little bit to the microphone? Thanks.
Well, I can repeat the question otherwise.
Does this also prevent model inversion attacks because you're using differential privacy during training, or is that, I can't picture where that's going.
Cool. Yeah, that's a great question. So the question is, since it's based on differential privacy, does it also provide differential privacy at training time and prevent attacks such as model inversion attacks? The answer as is no. At least there's no formal guarantee that we can get on the trained model. I think it might be possible to adapt it a bit to get some, but I think they would not be very good, and it's clearly not the best way to get differential privacy at learning time. Yeah. So it's purely at prediction time that we get the guarantees from. And we do train with noise to get good predictions, but not in a way that gives differential privacy.
Further questions? Please. Wait, you can use mine.
Thanks a lot for the talk. It was a very nice talk. So I'm not so familiar with this sort of topic. So it may be a very naive question, but like it seems that you are sort of preventing attacks, like additive attacks, with small norm, right?
Yes.
Because intuitively this should model like the act of modifying an image so that the naked eye cannot really distinguish it from the original. But cannot you modify an image like by, for example, modifying 1 pixel, but like very drastically so that the norm actually is not very small, but still the naked eye cannot distinguish?
Yeah, that's a great question. So here I focused mostly on norm 2 attacks, which is like where we did most of the work. But what you're describing would be maybe a norm 1 attack, where you count the power of the attacker by just the size of how much they change the pixel. So they could change like a few pixels by a lot. It's pretty easy to fit that in the framework and get guarantees against those attacks too. Maybe not both at the same time. But there's other norms to measure attacks that are harder to support under this framework, but still, I think with some work, we could do it. I think like kind of a follow-up thing that would be really interesting is to measure the power of the attacker in a more meaningful way than just like the norm of how much they change the pixels. But as far as I know, that's still an open question how to do that.
Okay, so let's thank the speaker again. Thank Matthias again.
Thanks.